Okay, in physics week 17, we will be doing fluid dynamics. So if you remember from week 4, we did regular dynamics with physical objects, and we analyzed how they move and how forces cause that movement. So this week we will be going over fluid dynamics, which is basically the dynamics of fluids, basically dealing with how fluids move. Okay, so let's get started. So the topics are types of fluid flow, the equation of continuity, Bernoulli's equation, and Poiseuille's equation. Okay, so the last one, I don't really know how to pronounce that, so excuse my pronunciation for that one. Okay, so those are the 4 topics for today. So let's get started with types of fluid flow. So there are 4 main categories we can sort fluid flow into. So the first one of those categories is stable flow versus non-stable flow. So before we get started with that, we need to analyze what factors cause fluid flow. What factors influence the flow of the fluid? So this could include the density rho, pressure on the fluid, the velocity of the fluid, all those things. Those are characteristics of fluid flow. Okay. So a stable fluid flow means that all of these things do not depend on time. So basically this means that we cannot write any of these items as a function of time. We can't say that, oh, the velocity of a certain molecule in the water depends on time, like sine of t. So for stable fluid flow, we cannot have something like this. The velocity of the fluid, the pressure, the density, they cannot depend on time. Okay. So one example where the fluid flow is non-stable is where we have the ocean, have a water molecule inside, and let's say every 3 seconds, a wave comes over. And in this case, the water molecule goes up with some kind of velocity v, and therefore the velocity depends on the time. So this is an example of non-stable fluid flow, and therefore, stable fluid flow, we cannot depend these values on time. But this doesn't mean that we can't change these values. We can still change them. They can still vary. They can still be different in various locations. But the only thing is they can't depend on time. So this means that we're going to, if I draw a little diagram here, we're going to look at this quite a bit later on. So if we have a larger tube constricting down to a smaller tube, we can see how the cross-section area of the tube, which is one of the factors of fluid flow, it changes, right? But it doesn't change with respect to time. It changes with respect to position. Okay, so this is one example of stable fluid flow. These factors depend on position, not time. So that's what stable versus non-stable means. Now I've got another type, which is called compressible versus non-compressible. So this is pretty self-explanatory. When a fluid is compressible, it means we can compress it down. If you remember from last week, I discussed about how the density of a fluid can change based on the pressure or the temperature of the fluid around it. So when we apply a pressure to a fluid, we can constrict it down by compressing it down. Okay, so when a fluid is compressible, it just means that we can compress it down, which means that its volume can change, which means that the density can change, because density is related to volume. So this means that, on the other hand, non-compressible means that these values can't change. We can't compress it down, which means we cannot change its volume nor its density. So for a non-compressible fluid, the density is constant. Right? So for fluids, almost all fluids that exist in the real world are compressible to a certain degree. Okay? For example, most gases are very compressible, and liquids are also compressible too. So all fluids are compressible. And it's virtually impossible to have a fluid that cannot be compressed under any degree. Okay? But the thing is, liquids are very, very difficult to compress. They can still be compressed, but it's very difficult to compress them. You need a ton of pressure to compress down a fluid. So in this case, we would take fluids as non-compressible. Not fluids, liquids. Okay, we would take liquids as non-compressible because they're so hard to compress that it really doesn't make any difference if we take them as compressible versus not compressible. Okay? So in most cases, we're going to consider our liquids as non-compressible because this simplifies things a lot. Okay? So that's the definition of compressible versus non-compressible. So now we have a third type of fluid flow. It's laminar versus turbulent flow. So laminar flow, I like to describe it as perfect flow. And this perfect flow is when, let me draw a little tube here. If the velocity of the fluid is this way, then laminar flow means that every single molecule in this fluid is going in a straight path perfectly, okay, parallel to the tube. Everything is perfect, okay? They're not interfering with each other. Every single molecule is going in the correct path, okay? So that's laminar or perfect flow. So obviously this is not realistic, and the opposite of laminar is turbulent. Turbulent flow is when maybe the water molecules spin around or they go backwards even. But although overall they're going forwards in the right direction, some of the molecules are jumbling up, they're going in wrong directions. So that's what we call turbulent flow. So most real life liquids, almost all of them have some degree of turbulence, okay? So turbulence is actually very hard to predict. So for today's lesson, we're going to be only focusing on laminar flow, because in laminar flow, everything is perfect and all the molecules are going in the right direction. Okay, so the fourth type of fluid flow is viscous versus non-viscous. And if you might have heard the word viscosity before, viscosity is basically the stickiness. How sticky this fluid is. For example, maple syrup has a very high viscosity. If you try to pour maple syrup out of a jar, it flows out very, very slowly. And so does honey, molasses, all those sticky things. Okay. On the other hand, water and milk or juice, those things are not viscous because they flow out very quickly. Okay. So that's the difference between viscous and non-viscous fluids. And some people have confusion between what is laminar, what is viscous. So laminar flow, remember, is when all the particles are going in the right direction. Viscosity is not caused by molecules crashing into each other or going in wrong directions. It's caused by intermolecular forces between the molecules. So in chemistry, you'll learn that the molecules have electrons and they repel each other, and all sorts of things go on between the molecules, and this force causes viscosity. Okay, so fluid's flow can be laminar, where all the molecules are going in the right direction, but it can be viscous as well. Okay, viscosity is not caused by the direction or paths of the fluid molecules. It's caused by the intermolecular forces between the molecules. Okay, so for today's lesson, we will only be looking at specific types of fluids. We're going to be looking at stable flow, non-compressible flow, and laminar flow. Those things have to be constant, because if it was compressible, then density would change. It'll get really complicated, and we would need to know thermodynamics to do that, okay? So we're going to keep these three things constant, these three assumptions, for all the fluids we analyze today, okay? But the last thing, viscous versus non-viscous, this thing may change, okay? Some of the problems we'll be dealing with non-viscous only, and some of the problems we'll be dealing with viscous fluids, okay? So those are the four types of fluid flow, and let's go on to the equation of continuity, okay? So this is the first equation we have for today, and this equation relates velocity, so the flow of the fluid, the velocity of that, to the cross-section area of the path of the fluid. For example, if we go back to this diagram I drew earlier, we have a wide tube narrowing down to a smaller tube, okay? So A is the cross-section area of the pipe here. Let's say this is A1, A2, and the cross-section area of the pipe has an impact on how fast the fluid flows. Okay, so the equation of continuity relates velocity of fluid to the cross-sectional area of the fluid's path. Okay, so to derive the equation of continuity, this relies on the fact that the mass flux, which is basically the amount of mass that passes a point anywhere in the pipe, okay, if we choose any point, the amount of mass that passes that point per unit time is constant, okay? So the amount of mass that's passing this area per time is the exact same as the mass passing this area per time. and this is constant for all fluids, okay? So if mass flux is, so the equation of continuity, we derive it from this theorem that the mass flux in any fluid is equal. Okay, so now we're going to use m equals rho v. Okay, so let's replace this with rho 1 v1, well not v1, delta v1 over t equals rho 2 delta v2 over t. So here, I turn the mass in terms of volume flux. So v1, delta v1 over t, delta v2 over t, that's the volume flux. Let's say delta v1 is right here. Delta v1 is the amount of volume that's going through this point per time, and delta v2 is going through this point, the amount of volume that goes through that point per unit time. Okay, and we multiply that by rho 1 and rho 2 respectively, the densities in each section of pipe. Okay, so this is because when the pipe constricts down, the density will change because there's a change in pressure on the fluid. Okay, so we got to consider the change in density as well. So now we have this equation, volume flux over time. And now we got to relate this to velocity somehow, right? So velocity, we know, equals to distance over time. And we know that volume with a big V equals distance times the cross-sectional area. So if we multiply this by the cross-sectional area, then what do we get? Volume over time. So this is the volume flux. So we can replace volume flux with A times V. So let's replace volume flux, these values, with A times V. So rho 1 A1 V1 equals rho 2 A2 V2. And this is the equation of continuity. Okay, so this equation relates the velocity to the density to the area, the cross-sectional area of the pipe the water is going through. Okay, but I said earlier that we're only going to consider non-compressible fluids in this class. So that means that the density is constant. So rho 1 will equal to rho 2 in our situations. And thus, they cancel out. A1 V1 equals A2 V2. So this is for incompressible fluids only. Because in this case, we have the densities equal and they cancel out. Okay, so this is the equation of continuity. For an incompressible fluid, which is all we're going to do today, we have A1 V1 equals A2 V2. So this equation will relate velocity to cross-section area. And you can see from here that the greater the area, the smaller the velocity, and the smaller the area, the greater the velocity. Okay, so you can see how the velocity was small in this wide pipe, and it got faster in the narrow pipe. All right, so we have these problems here, 2 problems. Pause the video if you would like to do these for yourself. And here's the solution, okay? So for this, the first one, we're going to use the equation of continuity once again. Since it's water, it's basically incompressible, right? Because all liquids are virtually incompressible, so we're going to consider them as incompressible. So the equation of continuity says that A1 V1 equals A2 V2. Let's say these 2 things are A1 and V1, and these 2 things are A2 and V2. So the A1 is going to be 0.01 squared times pi, because that's the area of a circle formula, times V1 equals to A2. So A2 is going to be 0.0025 squared times pi times V2. And we know that V1 is 5. Now we have an equation with only V2 inside it. V2 will equal to 80 meters per second. All right. So that's the first problem. All we had to do was directly apply the equation of continuity. Now for the second one, it's a little more tricky because it's not in the pipe anymore. We have to consider the air in a room. So for this problem, you have to adjust the situation so that you can use it to work with the equation of continuity. A1 V1 equals A2 V2. There's not really an A2 V2 in this situation, so we got to change up the situation so that we can apply to the equation of continuity. Okay, so how would we do that? Well, if we draw out the room, it's going to be kind of like a rectangular prism. 5 by 4.5 by 9.2. So let's say the air has to go through this way. So we can visualize this room as almost like a pipe, and the air is going really, really slowly through this pipe. So in the case of the room, the area here is the cross-section area, 5 times 4.5. And the velocity is the distance here, traveled by the air per amount of time. So it's going to be 9.2 divided by the amount of time it takes, which is 16 minutes. So to turn that into seconds, we get 16 times 60. Okay, so now we deal with the other side. Same thing, we got 0.075 squared times pi times v1. All right, so now we've got only v1 in our equation, and we can just solve. So let me solve it for 1 second. 5 times 4.5 times 9.2 divided by 16 divided by 60 divided by pi divided by 0.075 by 0.075, and you should get v1. Hold up a second. I think v1 should be around 3 meters per second. All right. Now we've got another problem. Pause the video if you want to do this for yourself. And here's the solution. So this is actually one of my more favorite phenomenons that go on with the equation of continuity. And it's that when you turn on the tap, the water is widest right here, and it gets narrower as it flows down. So you can try this out in your own home. You can do it in your kitchen. You can go to the bathroom, turn on the tap, and you will see how this works. So why does it work? Well, we can use the equation of continuity. A1 V1 equals A2 V2. This says that the higher the velocity, the smaller the cross-section area. And as you can see here, the velocity right at the tap is smaller than the velocity down below because gravity accelerates the water as it goes down. Since the velocity is higher here, that means the area must be smaller here as well. Okay, so that's why the area is smaller than up at top. Okay, so that's part A. Now part B, we'll just apply this formula, okay? So we have A1 V1 equals A2 V2. Let's say these things are A1 and V1. So A1 is going to be 0.075 squared times pi V1. Well, V1 is given, so that's 2. Now we want to find A2, so we can get the diameter, okay? A2 times, well now, what's V2? How do we find the velocity of the water down here? Well, we can use kinematics, right? Water is a particle. All the kinematics laws still apply to water. So we can just use the equation v squared equals v0 squared plus 2ad. So it's going to be v squared equals 2 squared plus 2 times 9.8 times 0.5. Your velocity should be around 3 meters a second. Right? So once you find your area, you'll be able to find your diameter by doing the area of a circle. So once you solve that, you're going to get D2. It's going to equal around 1.2 centimeters. All right. So as you can see here, mathematically, we can calculate why, like we can show it in numerical values, how the diameter is bigger at the top and smaller at the bottom. Okay, so now we move on to the second equation of today. This is the most important equation, actually. This is called Bernoulli's equation. And Bernoulli's equation connects pressure to flow velocity to the height of the fluid. Okay, so it connects all three of those things. And Bernoulli's equation depends on what we call Bernoulli's principle. And the principle is stated right here. The higher the flow velocity, the lower the pressure, and the lower the velocity, the higher the pressure. So let me draw out this diagram again. From the equation of continuity, we know that it's faster here than here. So the Bernoulli's principle says that the higher the flow velocity, the lower the pressure. So P is low here, P is high here. So there's a higher pressure going this way than here. Okay, so this is actually a little bit counterintuitive, right? You might think that the higher velocity, the higher the pressure. But this isn't true, because if the velocity was higher where the pressure was higher, then the pressure vectors would look like this, and there would be a net pressure going left or a net force going left. And this opposes the motion of the water, and it's going to slow it down. So obviously this can't be true, right? Because the water needs to flow, still keep flowing, okay? So the reality is, the higher the flow velocity, the lower the pressure, so that there's a net pressure going to the left and a net force going to the left, okay? So you may ask, hey, if there's a net force going to the left, going to the right, why isn't the water speeding up, right? Because it's going to accelerate. So this is where viscosity comes in, okay? So viscosity creates internal friction, and we know how viscous fluids flow a lot slower. And this is because the internal friction inside the fluid slows it down. So the internal friction of any kind of realistic fluid is going to give a backwards force against the motion. And this kind of balances out the pressure and the viscosity, okay? And when they balance out, we kind of get a constant velocity, all right? This is Bernoulli's principle. The pressure is higher for low velocity and lower for high velocity, okay? So Bernoulli's equation is the equation we derive from Bernoulli's principle, okay? So to prove Bernoulli's equation, I'm going to draw out a little wacky diagram here. Because Bernoulli's equation, as we remember, it relates pressure to velocity to height. So let's say this is H2, and we have H1 here. We also have A1, A2, V2, V1. What else do we have? Not much else. Oh, we got P1 and P2 too. All right. So to prove Bernoulli's equation, we're going to use the conservation of energy. And the conservation of energy says that work done equals change in kinetic energy. Because we have the change in kinetic energy from V1 to V2, so we can relate the work to the kinetic energy. Right? So how do we calculate the work? Well, we got to look at all the work acting on this section of water. So the first work I can see is that we have a pressure, P1, going inwards. And it's in the same direction as the flow velocity, so we take that as positive work. So the work done by P1 is going to be P1 times A1, so that gets us to our force, multiplied by some kind of D1, where the distance is applied, okay? So that's the work done by P1. What else work? Well, we have work from the other pressure, and it's going in the opposite direction, all right? It's going in the opposite direction of the fluid flow. We take this work as negative. So we got to do minus P2, A2, D2. And what else is there? One last component of work is the gravitational work, because when the fluid velocity goes up, gravity does negative work on the water. So we have to subtract mg times h2 minus h1, right? Because we have the force and the distance this force is being applied. So this is the net work on the water, and this equals the change in kinetic energy, which is 1/2 mv2 squared minus 1/2 mv1 squared. All right. So now let's clean this up a little bit, and we will rearrange this formula, this equation, to get to a nicer equation. Okay. Let me clean this up real quick. The first thing we're going to do is we're going to divide through everything by m. Since we have 3 terms with m here, it's reasonable to get rid of them. So we're going to have P1 A1 D1 over m minus P2 A2 D2 over m minus GH2 plus GH1 equals 1/2 V2 squared minus 1/2 V1 squared. Okay, so now we can use m equals rho V, or m equals rho times A times D. Okay, so we can replace the m's in here with rho AD. Oh, and look at that. These cancel out. Now let's multiply everything by rho. We're going to have P1 minus P2 equals minus rho GH2 plus rho gh1 equals 1/2 rho v2 squared minus 1/2 rho v1 squared. So now I'm going to rearrange it so that we get all the components with a 1 on one side and then all the components with a 2 labeled at the bottom on the other side. Okay, so rearranging, we're going to get p1 plus 1/2 rho v1 squared plus rho gh1 equals p2 plus 1/2 rho v2 squared plus rho gh2. And this is Bernoulli's equation. You can see how this relates the pressure to the velocity to the height. Okay, so this is very important equation, and a good way I like to memorize this is by seeing how this section of each part of the formula looks a lot like the regular kinetic energy formulas. That's the kinetic energy, and this is the regular gravitational potential energy. And these look a lot like them. So a good way I have to memorize them is I replace m with rho in these equations, and then we add the pressures on either side. So this is Bernoulli's equation. Okay. So before we go on to problems, I need to specify the conditions we need to have to use Bernoulli's equation. As we know, all the fluids we analyze today are going to have to be laminar, they have to be stable, and non-compressible. As you can see here, that's why I had a constant rho here. See how there's no rho 1, rho 2? Okay, so that's why we have to keep a constant density so that it's non-compressible. So we can only use Bernoulli's equation for non-compressible fluids. Another thing is that we cannot have viscosity. Although Bernoulli's principle can have viscosity in it, Bernoulli's equation cannot. Because as you can see here, when I calculated the work, I did not calculate the work done by the viscosity. Because, as I said before, viscosity is internal friction, and it does work to slow the fluid down. And as you can see here, I did not include that in my initial work equation, and therefore we cannot have any viscosity to use Bernoulli's equation. Right? So before we go on, I want to clear up something about Bernoulli's equation. So when I at first learned it, I was confused because I thought, oh, Bernoulli's equation is derived from this really, really wacky tube. And does that mean that Bernoulli's equation can only be applied to something like this? No, Bernoulli's equation, as long as there's pressure, as long as there's a velocity, or it doesn't even need to have a velocity, okay? It doesn't matter what kind of situation it is. So one common example is if we have an airplane. We always wonder, how do airplanes fly, right? How do they get lifted up? So for an airplane, the wings, this is like a cross-section of a wing. It's very, very specially shaped so that the velocity up here is high and the velocity down below is low. I don't know how to do that, but they do it, okay? So as you can see here, we have two regions of air, and we can apply Bernoulli's equation to these two regions, okay? Bernoulli's equation doesn't have to be with a really wacky pipe. As long as there's two different regions of fluid, we can compare them with Bernoulli's equation, and that must be constant for these areas of fluid because they're connected together, okay? They're both in the same body of air, okay? So in this case, since they're basically on the same height, we can ignore the rho gh part, and we can see how P plus 1/2 PV P plus 1/2 rho V has to stay constant for the top and the bottom. So this means that since the velocity is low down below, the pressure is higher down below. And therefore, there's a net pressure going up, which will create lift. All right, so that's how Bernoulli's equation can relate to airplanes. All right, so Bernoulli's equation can be applied to any situation where there's a variation in pressure, velocity, or height. Okay, so that's how you would use Bernoulli's equation. It's a very useful equation. Okay, so let's go into some problems. Pause the video if you'd like to work these out for yourself. Okay, so here's the solution. So for the first problem, it's always better to draw out a diagram. with a really, really wide tank, and water is going to flow out from a hole at the bottom of the tank with some kind of velocity. I want to find the velocity there. Okay, so for this equation, for this situation, we can use Bernoulli's equation between this region of water and the bottom region of water. Okay, so if we apply Bernoulli's equation to the top region of water, this means that the pressure plus 1/2 rho v squared plus rho gh. So what's the pressure right here on the top? Well, the only pressure is atmospheric pressure, so we're going to do PATM. Now, what's the velocity? Well, since it's a very wide tank, this means that the velocity of the water going down is very slow, right? Because according to the equation of continuity, A1 V1 equals A2 V2. And if this area is very small compared to this area, then basically we can neglect the velocity of the water up here. So we can take that out of the equation for the top. And then we have rho gh. Now let's take h down below. And h equals 4.6 here. That's given in the problem. So we're going to have to add rho times g times 4.6. Okay, so that's Bernoulli's equation for the top. Now we got to look at Bernoulli's equation for the bottom. At the bottom here, what's the pressure acting on the water right here? Well, of course, there's always going to be atmospheric pressure, so it's PATM. So now it gets complicated. Do we consider the gauge pressure here? Right, there is going to be pressure. There's a whole column of water above this thing. Are we going to include the gauge pressure? And the thing is, we don't consider it. So you may ask, why? Well, from last week, pressure, we can visualize pressure as a thin plate holding a ton of water above it. That's how pressure is created, okay? So if we were to look at the hole where the water is coming out, this is kind of like a magnified version of the hole. If we have a thin plate right here along with the hole and the water is going down, the thin plate is also going down. They're both going down at the same rate. The thin plate cannot support up the water because it's also falling down, okay? So this is almost like, since they're both in free fall, there's no relative, they're both falling. So the plate cannot support any water. This is almost like if you were to go skydiving and you were to hold a very heavy object like a piano, and you and the piano are both falling in the air. Since you're both in free fall, you don't really need to hold up the piano at all, right? Even if you are holding the piano, it feels weightless. Right, guys? Since you're both falling, there's not really a weight. So the apparent weight of the piano is 0. So the apparent pressure, the apparent gauge pressure here on the plate is 0. So we don't include the gauge pressure from the water here. So the only pressure is PATM. So now let's add that to rho v. 1/2 rho v squared. And since h is 0 at this point, we don't include that. So this must equal to this. So let's equate them. PATM cancels out, so we get rho g times 4.6 is 1/2 rho v squared, canceling out rho v equals the square root of 2g times 4.6, and calculating that, 2 times 9.8 times 4.6, take the square root, v equals 9.5 meters per second. All right, so that's a very common example of Bernoulli's equation, right? So one thing you might note about this is you can see how v equals the square root of 2gh. If we use conservation of energy, remember back in week 7, I think, for conservation of energy, we know that 1/2 mv squared equals 1/2 mgh. And we get the same result, v equals the square root of 2gh. And this is basically how we can tie fluids with regular objects falling from a height h, because the fluid is also a particle, so the velocity is also 2gh. Let's go on to the second problem. This is basically the same thing. So we're going to analyze Bernoulli's equation at the top and at the hole. So at the top, we got pressure, PATM, added to the velocity. Well, since it's a very large opening at the top, the relative velocity is 0, so we don't even consider that. Now we got to add rho g h. So let's take h equals 0 right here at the point where the water comes out, which means that the h right here at the top is h, lowercase h. Okay, this must equal to Bernoulli's equation at this point. Remember, we're not going to add the gauge pressure in, so it's just PATM plus 1/2 rho v squared. And since we said h equals 0 at this point, there's no rho GH term. So once again, canceling stuff, V equals the square root of 2GH. And just like the problem we did beforehand, this is the equation for the velocity of water coming out at a hole a distance h below the surface of the water. And this is called Torricelli's principle, Torricelli's theorem, okay? Because this is so well known. This is basically a special case of Bernoulli's equation, okay? Let's go on to 2 more problems. Pause the video if you'd like to do this for yourself. All right, here's the solution. So the water from a fire hose can spray to a height of 15 meters. What's the gauge pressure in the hose? So first of all, we have the hose down here. And there's a really high pressure in here. And then if we look at the water, it streams up and it comes down. Okay, it goes all the way up and comes down. I'm not very good at drawing this. So it goes up, it stops, and it comes down again. And now let's look at Bernoulli's equation between this point and this point. So you may see how I'm comparing Bernoulli's equation between 2 points, just like the conservation of energy. And this is because Bernoulli's equation is the conservation of energy. So the strategy we use for them is very similar. Okay, so we're taking Bernoulli's equation at the top and Bernoulli's equation at the bottom. Let's first do the top. The top, well, the pressure is PATM. All right, PATM. Then we have to add rho G, 1/2 rho V squared. Well, there's no instantaneous velocity there, so we don't need to include that. And then we've got rho GH, and this is the height. Okay, so then you relate this to his equation at the bottom. Well, at the bottom, we got PATM as well, plus the gauge pressure now, because there has to be some kind of gauge pressure in there to lift up the water, okay? Plus the gauge pressure. And there's no net velocity in here. There's no net, there's no height either, because h is 0 right here. So we don't even include any of those other terms. So solving, we get PG equals rho GH. Okay, so it's 9.8 times 1,000 times 15. It's going to be 147,000 pascals. Okay, so we've got one more example here. During a storm, the wind blows at 35 meters a second. So what's the net force acting on the roof? Well, this is a lot like the situation with the airplane. So let's say this is the house. Now looking at the house. So we got wind blowing at some kind of velocity up there, and there's no velocity inside the house. So using Bernoulli's equation, we can compare the air between these 2 points, okay? And if we compare the air there, we can find the difference in pressure. So the P is lower here, and P is higher here, because Bernoulli's principle says that the lower the velocity, the higher the pressure. The higher the velocity, the lower the pressure. Okay, so since P low, P high, we can find the difference in pressure, and therefore we can use that to find the net force pushing the roof up. So now let's do Bernoulli's equation on the top and bottom. Top, we got the pressure. That's what we want to find. And we've got 1/2 rho V squared, and then we have to add rho GH. But the thing is, there's actually not really that much distance between these 2 things, right? Since there's only like a wall separating them, the area between, or the distance between these 2 regions is very minimal. So we don't even need to consider the difference in height. So now we add this to Bernoulli's equation inside the house, which is, inside the house, it's obviously P at atmospheric pressure. Otherwise, you would not feel very comfortable in there. And then we would have to add nothing else, because there's no velocity, there's no net difference in height either. Okay, so we got the pressure right here. This is P right here. P equals PATM minus 1/2 rho V squared. And using rho equals 1.29 for air, we're going to get 0.5 times 1.29 times 35 times 35. It's going to be PATM minus 790. So I'm going to keep this in this form. You're going to see why I did this later on. So the pressure outside is this quantity. So to find the net pressure, we have to subtract. We have to do PATM minus P. So we're going to do PATM minus this quantity. And as you can see here, PATMs will cancel out. We get 790 equals net pressure going up. And we know that P times A equals force. So we're going to get 790 times 240, 1896.00 newtons upwards. And that is a huge force. So that's why if during a storm, that's why your roof might blow off during a storm, because of Bernoulli's equation. Okay, it's not because the wind can tear the roof off or anything. It's because of Bernoulli's equation. Okay. So now we've got two more problems. The first one is pretty fun. It's about airplanes. And I'll give you a second to do this and pause the video if you want to do this for yourself. All right, so here's the solution. This is much like the problem we just did. We're going to compare Bernoulli's equation between the top of the wing and the bottom of the wing. So we're going to look at Bernoulli's equation here, Bernoulli's equation here. So we've got 150 meters a second here and 260 here. Let's say this is V1 and V2. Okay. So we want to find P1, P2, find the net pressure on the wing, and then we can use that to find the net force on the wing. Okay. So using Bernoulli's equation, we got P1 plus 1/2 rho V1 squared. And since there's no great difference in height there, we can neglect the height difference. So this will equal to P2 plus 1/2 rho V2 squared. All right. So the net pressure, the difference in pressure, is going to be P2 minus P1. So rearranging it a bit, we got P2 minus P1 equals to 1/2 rho V1 squared minus V2 squared. Okay, so let's calculate that. What is V1 squared minus V2 squared times 0.5 times 1.29. So the net pressure, 29089. Okay, so that's the net pressure on the wings. And now we can use this to translate to the force. P equals P times A, force. So the total area of the wings, one wing is 78, so two wings is 78 times 2, 156. So we multiply this to 29. I'm going to take that as 30,000 actually, times 156. We're going to get 468,000, not thousand, I think that's 4 million newtons. All right. Now we divide by 9.8 to get how much weight, how much mass this can handle. This is around 477,551 kilograms. I don't think that is realistic though. So we'll take it from this problem. All right. So that's the first one. Now for the second one. Inside a hurricane, the speeds are high. Outside, the speeds are low. So creates a difference in air pressure. So let's solve for that. So let's say that this is the hurricane cylinder. So we have high velocity here, which means lower pressure, and low velocity here, B equals 0 outside. Okay. So let's use Bernoulli's equation. First of all, let's look at the air outside. So that's going to be PATM, and that's it, right? There's not a difference in height either. This is going to equal to P inside plus 1/2 rho V squared. So Pn is just going to equal to PATM minus 1/2 rho V squared. So first turning velocity into meters per second by dividing by 3.6, squaring that times 1.29 times 0.5. I'm going to do 1.013 times 10 to the 5th. Subtracted that. Then we get P in equals 968.20 pascals. Okay. So those are the two applications of Bernoulli's equation. All right, so now let's move on to the third equation for today, and this is Poiseuille's equation. Okay, so Poiseuille's equation, this is the only equation we're going to do today that considers viscosity. Okay, so this equation relates Q, which is volume flow per time. So this is the amount of volume that passes every point in the pipe per time, which is Q. And this relates Q to R, to P1, P2, to N, to L. So I'm going to tell you guys what these things are later on. So this equation is given by pi times R to the fourth times P1 minus P2 divided by 8 L. So first of all, R is the radius. P1 minus P2, what that is this is the pressure difference between the ends of the pipe. So when we use this equation, we're going to cut off a section of pipe, and we're going to take the pressure difference on either side. So let's say the pressure is here, P1 and P2. Okay, so why do we need a pressure difference? Well, since there's internal viscosity, this causes internal friction, which the pressure needs to overcome. So that's why we need the pressure here. That's why we need the pressure difference, okay? So that's what P1 and P2 is for. That's the pressure difference on either side of the length of pipe. And then we have 8 and N. N is the viscosity. This is, much like density or other things, this is a constant that is given for specific materials, okay? You can see how we have viscosities in this table right here. Don't need to worry about these tables, these values, don't need to memorize them either. The problem is always going to give you it, okay? So as you can see here, viscosity is in the units pascals per second, pascals times second. And finally, we have L. L is the length of the pipe, okay? So why we need L is because the pressure differences, they depend on the length. Because if let's say we had a very long pipe, we had a pump right here that maintained a high pressure and zero pressure right here. Obviously, the pressure is going to decrease as we go to the right, which is basically why we need to consider cutting off. If we cut off a section of pipe here, we need to consider how long it is as well. So that's why we have P1 minus P2 in terms of L. So that's why all of these values are critical to the volume flow rate. So you can see how this equation does make sense, because if the radius is bigger, the more flow you can have. The higher the pressure, the faster the fluid will go through. The lower the velocity, the higher the volume flow rate, because, well, obviously if it's lower, then just like water versus maple syrup, it will flow a lot faster. And finally, we have L, okay? So the rigorous proof for this equation gets really complicated, and you will need calculus for that. So I am not going to derive it here. But you can see how this works by doing some dimensional analysis on this. So if you would like, you can do some dimensional analysis later on your own time for this equation, and you'll see how it works out in the end, okay? So the actual thing is that this equation is rarely used in physics competitions, and I don't think you're even going to find this in the Physics 1 test, okay? This equation is actually not very well used, so you don't really need to memorize the whole thing, okay? It's always best to memorize it, but you don't really need to, okay? But the one thing you should know from this equation is that r to the fourth power is proportional to q. R to the fourth. Okay, some people may think that it's r squared, right? Because it depends on the cross-sectional area, but no, it is r to the fourth. Okay, so that's one thing you guys should know. Okay, so that is the equation, and let's do some problems. Okay, so pause the video if you want to do this for yourself. Okay, so here's the solution. We know that Q from Poiseuille's equation, Q is proportional to r to the fourth. So the ratio of the radii, which is the same thing as the ratio of the diameters, is proportional to the ratio of the volume flow rate and how fast you can fill up the pool. So Q is actually proportional to 1 over time, because Q is equal to volume over time. So 1 over time, or time, is proportional to 1 over r to the fourth. So the ratio, the ratio of the radii is the reciprocal of that to the fourth power is equal to the ratio between the times. So the time ratio equals R2 to the fourth over R1 to the fourth. So let's say R2 is this equation, this part, and R1 is this part. So doing that, we're going to have 5 over 3 to the fourth power, take the reciprocal, multiplied by 4. We're going to have around 30 minutes. Okay? So now for the last one, this is basically a direct application of Poiseuille's equation. We're going to have Q equal to, what is that? Pi r to the fourth, P1 minus P2, by 8 and L. So what is the volume flow rate? Well, the volume flow rate is change in velocity, or change in volume over time. So it's just the volume of the whole room divided by time. There's going to be 9 times 12 times 4 divided by 10 times 60. Okay, so 9 times 12 times 4 divided by 10 divided by 60, 0.72. We know that Q equals 0.72. So what do we need to solve for? We need to find the diameter of the air duct. So we're going to have to isolate R in this equation. So R to the fourth equals Q8QNL over pi times the pressure difference. All right. So all we're going to do is plug in values now. Let's clear up a little space. So we're going to have 8 times 0.72 multiplied by the length of the pipe divided by pi times the pressure difference. Okay. So the pressure difference is equal to 72 pascals, which is right here. And I forgot about the viscosity. Let's multiply that in as well. Okay, so this will equal to R to the fourth power. Let's quickly solve that. Okay, and take the quartic root, take the fourth root of that. We're going to get R equals 0.056 meters. And multiplying by 2 to get the diameter, that's around 11.1 centimeters. Alrighty. So that's it for fluids. Okay, so here I have a slide of all the formulas from last week and this week. So you can take a screenshot of this or whatever you need for your study needs. Okay. So once you've taken a screenshot of that, that'll be the end of this class. So thanks for listening, and I'll see you guys next time.